And today is a chance for us to challenge ideas and expand our knowledge. We have 10 invited lecturers including the online lecture and 18 presentations by research scholars and faculty members from across the different states. Before we begin, I would like to extend my heartfelt gratitude to the university authorities, department and university officials, our invited speakers, the organizing committee, and students and everyone who has contributed to making this seminar a reality. Without your dedication and hard work, this event would not have been possible. With that, let us embark on a journey through the fascinating world of number theory and algebra. I wish all a productive and inspiring seminar. Thank you. Thank you, sir.
Thank you, sir, for your valuable suggestions and words. I hope with these new things, as what Professor Conrad, Professor P.K. Roy has told, that we shall go through with the interaction and close interaction with the participants. We shall take this seminar to that level. So now I request to our guest of honor, Dr. Nupra Sahu, the registered Sambalpur University, to address the gathering. Sir.
Respected the chief guest of the occasion, our PG Council Chairman and Church Vice Chancellor, Professor T.K. Das, the HOD and the President of this committee, Professor P.K. Tripathi, the convener of this seminar, Professor P.K. Roy, the veteran professors sitting before me, who belong to this department, other departments, and professors and guests coming from NIT, Nigeria, other different mathematical institutions, the guests and participants online, and dear students and scholars. The professors are here, very well known, and I have seen and many of the students also, who are in the fourth or third or fourth semester, they also know that I have told them earlier that I have passed in mathematics only for once in my career, in my life, and that was in matriculation. Neither before, no question after. And my teachers told me, facts about mathematics. And I hope that you will also find it beautifully and interesting. But after I passed my matriculation, I had a deep desire to know the intricacies of the mathematics. And since then, sometimes whenever I get any material relating to mathematics, I do delve into those aspects. I want to know what are the things, whether I could understand those theories or principles laid down in the mathematics. And I have a kind of fascination also for mathematics nowadays. As it was indicated earlier by when the introduction was being given by the convener, that mathematics is the language of the universe, it's the language of the nature. And if it is the language of the universe, everything comes inside the universe, within the jurisdiction of the universe, and mathematics becomes and becomes definitely the language of everything else. So it encircles and engulfs the entire gamut of the universal system. You cannot think forms, it constitutes the basis, rock foundation, on which any other subjects, any other topics, any other disciplines that stand up. So this is definitely the nature of the language of the nature and the universe. And mathematics is such a subject. The topic relates to the universal truth. The truth doesn't differ from locations or from times or from ages. There are developments, there are progresses in different ways related to mathematics also. But the truth, the underlying truth, is always the same. 2 plus 2 is equal to 4. It is there everywhere. Everywhere. Universally, it is the truth. That's why mathematics carries so much of relevance and significance in all times and in all ages. If you think of, because you are talking of the number theory, let me start from the number 0. And all of you know that 0 was discovered by the Indian scientists. It was discovered in the Indian soil. And the contribution of 0 to the world, the universe, is quite revolutionary. Had there been no 0, you cannot think about it. The everything value of 0 is very much. Then comes from 0 to directly to the infinity. And infinity is not a number. Just remaining, just talking your activism that infinity is not a number, but it's a concept. Because it's infinite. And then if you just come back, you'll be finding mathematics beautiful. Not my wisdom, which are quite interesting. I may that all of you know about the hypothesis sequence. What is there? That is sequences that goes. That they do not consider. It is a beautiful. And the sequence is 0, 1, it becomes 1. 1 and 2 becomes 3. 3 and 2 becomes 5. 5 and 3 becomes 8. This ways. It goes. And then there is and you find what single different aspects in the formation of the iron ores, in the formation of the leaves, in the formation of the galaxy, you'll find, and even if you find in the spectral formation of the species. And it is also available in the computer science and in the market, financial markets. Then if you think of the golden ratio, you will see the golden ratio. The average or the approximate average of Europe and 1.618. And this golden ratio, and you will be discovering not only in the field of computer science, you will be discovering the beauty of the field of artificial intelligence. That is 1.618, that's the golden ratio. And if you find that irrational that lie it is not a study. And what it doesn't end anywhere. I is irrational. And it goes you cannot finish it. And trillions of digits you end up being multiplying the solution of the convolution of the illusion. It's an illusion. You cannot find the solution when you want to calculate it. These are some of the things. And you have also, all of you know, the computer psychology. What is the computer psychology? It is a kind of equation, a very good equation, where high important numbers are linked to find out a simple and all of you, they are I1 and G. E is universal number, and universal number is generally approximately 2.718. And then you have the I is a imaginary identity. And I is I square is equal to minus 1. And you have also the I. And approximately the value of I there is 3.14159. And then you have the 1. One is the multiplication of the identity, and the 0 is the identity. So you working together is and you have also so many hypotheses, so many theories which are still there. Remember the fixed object. The Riemann hypothesis. You know the Riemann hypothesis that you cannot reach this conclusion. It is still a puzzle. And Riemann hypothesis, all of you know that to solve this problem, I find the counter proof. $1 million. $1 million. Highly important to find out the solution of the Riemann hypothesis. And you also cannot find the solution to the problem. P plus N. E plus NP, what does it mean? That if you find the solution of the problem very quickly, then you solve it very quickly. That's again the process. And so these are some of the good things that are here. And so these are come very fascinating subject, very intriguing subject, and very complex. And especially now, not many things have happened in the mathematics, where many of these things like these are. And the reason is that now we are in the age of quantum physics, quantum mechanics, and the classical physics that was there is no more relevant. The relevance is there, but the more significance you find in the quantum physics, where the atoms, the subatoms, the molecules, was at the tiniest level under the conditions. And then the quantum physics that when tomorrow there is the science day, scientists what do you think? That is means that we through the classical check on the light spectrum that he gives there that in the light has there's change in the system, there's change in the quality of the particle. And when it is spectrum, because it comes in contact with the radius of equations of different objects, and similar, who's there? He proves that light quantum is a light quantum, and there is also the energy level of the atoms. Light is quantum. Then he proves that he gets the Nobel Prize. He also gets the marathon. And the Rourkela was very much discovered in the 1980s. So this way, mathematics also progressed exponentially nowadays. So nothing more to speak because the system is changing, science is changing exponentially, and life is just different dynamics will be changing serially. And when the life itself becomes unpredictable, mathematics being unpredictable sometimes is not a big thing. We have but it's for all us and the students who are working on these principles. And we have also the so these are some of the theories, these are some of the mathematical principles which we have to just further keep in mind. Among this, not the aspects will be touched and the beauties of the mathematics. So I expect that the seminar which you are going to do this will be definitely successful. It's going to be wonderful. Do this for all of you, and you will be not because of the experts are here, the experts are here online, and we will be benefiting a lot. I wish all the best, all of you, for this good seminar.
you, sir, your valuable suggestions and encouragement to our students. Of course, at the beginning, Sir has told that he does not know anything in mathematics. That is, he is not good in mathematics. Of course, Sir has told like this. But after his speech, you might think of that he knows mathematics. But actually, if he never told that he don't know, he does not know about the mathematics, then definitely you might have thought of that he belongs to the mathematics field. Anyway, we are on the same number, even though he has the register, but he knows many things about mathematics. Thank you, sir, once again for your valuable questions. So now I take this opportunity to invite as well as to request our honorable chief guest, Professor Ikeda, Chairman of the Council. Also, he is the in charge of Vice Chancellor of Sambalpur University, and I request him to address the gathering also about the seminar. Sir.
President of the National Center, Madam 25, Professor Rourkela, esteemed register, Dr. respected commander of the seminar, Professor Algebra, senior retired faculty members of the department, my faculty colleagues from other departments, ex-students of this particular department, research scholars, and very dear students. As my predecessors have already told different aspects of this particular seminar, I am not going to touch those parts. But the theme of this seminar, that is number 3 and algebra, algebra, told me twice. I think this, I was checking, and it is talking about the symmetricity and which we find different fields in science, particularly physics, as the department was telling, and a number of discussions on different aspects of this particular new aspect of this particular seminar theory, that is number theory and live algebra. I think we put different questions and different aspects which will be taken care by the faculty members, the research scholars and students in this 2 days discussion. And I think it will be fruitful as part of the university if something will be taken from this particular seminar. I will not tell much as I am not expert on this particular field. Thank you very much. Thank you the organizers, the head of the department, and all faculty members for organizing such a wonderful seminar. Thank you very much.
Thank you, sir. So now I request Professor Savita and Dr. Sir to introduce our chief guest, Professor Debrecen, and guest of honor, our registrar, Sir Dr. Professor. I request Madam and Sir. Thank you, Madam, and Rajna. So already we are running late to start our national seminar. So without any delay, within a few seconds, we are going to start our as usual seminar. So for 3 seconds, I myself from Department of Head of Mathematics, I thank to our today's guest, Professor Viswanath for his valuable time spent with us to make this inaugural ceremony a success. Also, I thank our Registrar Sambalpur University Dr. Prof. Sausa as today's guest of honor, and his presence, his motivation to the students, definitely students will be inspired with this to read some more mathematics. And due to his valuable time and his interest and cooperation to make this program success, from my whole heart, I once again thank our registrars. Also, I thank the organizer, convener, Professor Peter Royce, for his efforts. For last 6 months, he has been putting his labor to make this seminar as a success. And he has taken all strengths to invite to all the participants to come to this program and to make it a success. I thank to our department colleagues, guest faculties, and our dear students for their valuable time to spend for us to make this seminar as a grand success. So also I thank our participants, invited speakers, those who have given their time to come to this seminar. And also I thank them from on behalf of the organizing committee, on behalf of the Department of Mathematics. And now the time has come to wind up this inaugural ceremony. And once again, I thank you all. But it is not a break. The inaugural ceremony is over. Now we shall start immediately within 5 minutes this national seminar. And I request the convener, Professor Peter, to start that program.
ସେଇଥିରେ ଗୁଗୁଲ ମିଟ୍ ଚାଲିବ ସାଉଣ୍ଡ ଶୁଭୁନି ସାଉଣ୍ଡ ଗୁଗୁଲ ମିଟ୍ ଚାଲିଛି ଏବେ ତୁ ୟୁଟ୍ୟୁବ ଦେ ଲାଗିଲା ପଛରେ ଏବେ ଲାଗିଲା ନାହିଁ ଫୋନ୍ ସେଟା ମୁଁ ବନ୍ଦ କରିବି ଭାଇ ମୋ ଫୋନ୍
some modifications to be done. So we will first start our online lecture and by Professor S. Viswanath, IMSc Chennai. I request Kesipati sir to chair this.
अरे मीट स्क्रीन टा खाली सेतरे जेमती करा है सेमती हां ठीक है हां आस्तिला
रंजन
ହେଲା ठीक ଅଛି
रंजन
ଆସିଲା ମତେ अरे ହେଲା ଥାଉ ଆପଣ
कोटा
ହେଇଛି ଦେଖନ୍ତୁ। प्रोजेक्ट कोणता असतो काढून हा होईल
Hello. Sir, if you can. Hello. Sir, please unmute yourself.
Hello. Can you hear me? Am I audible?
So which is
Professor Viswanath. Yeah. Can you hear me?
Yeah, I can hear you.
Hello.
Yeah. I can hear you. Yes. Am I audible?
Yes, we can hear you.
Okay. So just let me know when I should start.
hello sir, you can start now.
Okay. Yeah. You can see my screen.
हेलो এটা বন্ধ করে দিও
Hello, Professor Hajdu. Can you hear me? Now you can share your screen, please.
Okay. Just a moment.
नहीं सेठी माइक टा बंद कले को आसे तार माइक बंद कले को आसे यार स्पीकर टा बंद कले को आसे स्पीकर से साउंड हां नहीं हां हेलो सर गुड आफ्टरनून प्रोफेसर हायदो
Good afternoon. Good morning for me. Yes.
Not audible? Sir, are you able to listen to me?
Yes, I can hear you.
Okay, sir. So the next talk is by Professor Lajos Hajdu. He is from University of Debrecen, Hungary. The title of his talk is Power Values of Products of Catalan Numbers. Sir, I request you to please start the talk.
Okay. Thank you very much. I would like to share my screen. I still have a little problem with that. Maybe now I can do that. I don't know. Could I share my screen?
Yes. Yes, sir. Yes.
No, maybe it would be nice to make it larger.
Yes, sir.
I try to make it larger. Maybe this way. Does it work?
Yes, sir. Yes, sir.
Okay. Maybe a little bit smaller. Well, I think this is the best I can do. Is it all right?
Okay, sir.
Okay, so
Yes,
shall I
yes.
start?
This is okay.
Yeah, so shall I start my talk?
Yes, sir. Please.
Okay, then thank you very much for the possibility to give a talk on this nice conference. I would like to thank the organizers, in particular Professor Prashanta Kumar Ray, for the possibility that I can give a talk here. And well, my topic will be some new results about Catalan numbers. You will see that this topic has roots in Diophantine number theory, also in combinatorics, and it is related to both to India and to Hungary. So I hope that you will like this topic. So then let me start. I will talk about power values of products of Catalan numbers and related results, related things. And well, this talk will really revolve around powers of Catalan numbers and related questions. So first I will give a short introduction, then I will talk about the square values of products of Catalan numbers, then I will make it more general, and I will talk about power values of products of Catalan numbers, and then I will make it even more general and talk about powerful values of products of Catalan numbers. And I would like to mention that the new results I will present are joint with Florian Luca, Szabolcs Tengely, and Maciej Ulasz. Okay, so to start with, I need to tell you what Catalan numbers are, though they are very well known. So Catalan numbers are just defined from central binomial coefficients. So you just take 2n, choose n for some n, and then of course what is 2n, choose n. You can think of it in many ways, of course, but maybe the best way to think of it will be just in the usual way. You have a numerator, denominator is just n factorial, and the numerator is just the product of integers from n plus 1 to 2n. So you have n numbers upstairs, n numbers downstairs, and that is the central binomial coefficient. But that what you do is that you cancel n plus 1 from the numerator, and in that way you get the nth Catalan number. It can be proved very easily that Catalan numbers are integers, so they are derived from binomial coefficients, central binomial coefficients, in this way. This representation will be useful, so at some points I will recall this definition because it will be really helpful. But it is also good to mention that Catalan numbers satisfy a recurrence formula. They, of course, have a lot of properties. So I just would like to mention that if you know the nth Catalan number, that to get the next Catalan number is rather simple. You only have to multiply with 2 times 2n plus 1 divided by m plus 2. Catalan numbers have a lot of important properties. Also in combinatorics, you can count many structures by Catalan numbers. I just mentioned just for interest that in his book Stanley in 2015 gave 214 different combinatorial structures which are counted by these Catalan numbers, so they really appear in many problems. Okay, so what can we say about Catalan numbers? Well, I already mentioned in the beginning of this slide that, well, there are not too many studies about Catalan numbers in the Diophantine sense. So their Diophantine properties are not really explored. In particular, if you compare Catalan numbers to other similar objects, like binomial coefficients or factorials, those objects, binomial coefficients, factorials, are very well studied, not like Catalan numbers. So let me mention just some results from this topic in this wider sense. Let me start with a famous result of Erdős and Selfridge from 1975, saying that the product of consecutive integers is never a power. Positive integers, of course, here, a beautiful result. And then one can mention results of Erdős and Graham. They obtained many results concerning square values of products of factorials. So you take products of factorials and you would like to get squares. What can you do then? Or generalizations of such results due to Bérces, Dujella, Sarola, Teidemann, and myself. This is much more recent results. Here you see products of factorials equal perfect powers, L's powers. L is arbitrary integer, is 2. So we obtain many results into that direction. So really, if you think of factorials, or I could also mention binomial coefficients or consecutive integers, so really you will see many results, but not for Catalan numbers. So in this talk, I shall mention some recent results concerning power values and related values of Catalan numbers, or more precisely, products of Catalan numbers. Okay. So, well, what does it mean? What shall I consider in this talk? Well, this will be the main object, or this right-hand side is z squared will be replaced by perfect powers and other things. So you just take product of distinct Catalan numbers. So of course it would be silly to take the same Catalan number, at least if you talk about squares. So we just take different Catalan numbers, and the product should be a square. Okay. Where C0 is equals to 1, so it can be omitted. The index can be 1 up to anything. And then as a first, well, I would say observation is that Bertrand's postulate implies that a Catalan number itself cannot be a perfect power, not even a powerful number if n is greater than or equal to 2. Well, the reason is, I just scroll back. Well, this is a very simple result, but just to start with, it is an interesting thing. Anyway, so what is Cn? Well, this is just a quotient. You have the product of integers from n plus 2 up to 2n in the numerator. You have n factor in the denominator. And then Bertrand's postulate just tells you that there is a prime between so there will be a prime in the numerator, and then this just implies that this prime cannot be cancelled by the denominator. So you will really easily get that the Cn has a prime divisor on power 1, and then that's it. It cannot be a square or power or anything. Okay, so this is easy, but what if you take products? So then it becomes, of course, much more interesting. And then you will see that there are in fact two cases, k equals 2 and k is larger than 2. So if you take only 2 terms here, or if you take more than 2 terms, it really makes a big difference. We could prove that if k equals 2, then this equation has no solution at all. Of course, in distinct indices, that is the product of 2 distinct Catalan numbers, cannot be a perfect square. How to prove this statement? Well, I forgot to mention in the beginning that my purpose is to show you some results, of course, from this topic, and at some points I would like to show some elements of the proofs, but I will do this only if it is not too technical. If it becomes too technical, then I will just point out the important tools or important arguments behind the proofs, but then I will not go into details. But here this is a very nice and simple proof, so here I can show you how it works. That is the sketch of the proof. So what you can do, you just take 2 Catalan numbers, it should be a square. You denote the first index by n, the second by n plus m, and then you write out what is this product. And then you will find that, okay, you have a full square part, and then you have this first term here. What is this first term? This is just this quotient. And the point is that the numerator is just the product of consecutive integers. So in the numerator, you have products of consecutive integers, a full product of consecutive integers. Okay, but 2 of them are cancelled. So altogether, you have a problem to solve. You should tell when a product of consecutive integers, just 2 are missing, is a perfect square. And then you are back to the result of Erdős and Selfridge if there are no missing terms. What if 1 term is missing? Then you could mention results of Sharada and Shori. And if 2 terms are missing, then you can use a very nice result of Mukhopadhyay and Shori. They could completely describe the products of consecutive integers. 2 are missing, such that this product is a full square. Of course, there are some possibilities. There is a list of solutions, but if you check that list, which is a finite list, then you will see that no Catalan product appears there. So the statement is just proved. the product of two Catalan numbers cannot be a perfect square. Here I just would like to mention that this is a big difference compared to factorials, because the product of two factorials can be a square infinitely often, which is very easy to see. You just take a1 factorial and then a2 factorial in a way that a2 is just a1 plus 1. Of course, then you have a1 factorial squared times a1 plus 1. And if a1 plus 1 happens to be a square, then of course you have infinitely many solutions here. So for factorials, you can have infinitely many solutions here, but not for Catalan numbers. Okay, so let's turn to the case when k is at least 3. We have a product of 3 or more Catalan numbers. And well, in that case, the product has infinitely many solutions. I mean, the product can be a perfect square in infinitely many cases. In this theorem, we didn't want to describe the number of solutions up to some x, nothing. We were only interested in proving that there are infinitely many solutions. If you allow 3 or more terms, then the product will be a square infinitely often. So what to do when k equals 3? Well, since we only would like to prove the infinitude of solutions, we can make arbitrary choices. What we did was, here you see we just took C2, and then so we fix the index, the first index to be 2, and then we take two consecutive indices. And then this product should be a square. We considered only this specific 3-term product of Catalan numbers. And then if you write out the left-hand side, that I don't give the details. If you write out the left-hand side, you will have a paired equation in U, of course, and in Z, which has infinitely many solutions in U. It is very easy to check that. So you have infinitely many solutions when k equals 3. What is the situation when k equals 4? Well, it is even better in some sense. No, you don't have to specify indices in any way. You just take 4 arbitrary indices. And it turns out that, in fact, you have some kind of families of solutions, or polynomial solutions, if you like, in the sense that if you parameterize, you can parameterize your indices, these 4 indices, we can parameterize with some parameter t. And for any such choice of the indices, for any t, we shall have a square product. Again, it is very easy to check it. So it is just an identity, but you can check that indeed for these choices, the left-hand side will be a square. The product will be a square. Okay, so we are done with k equals 4. And it will be very important that here we have really a parametric solution. What is the situation when k equals 5? You see, I will not go till infinity one by one, so we shall finish the proof soon, but this is again some special case. This is the last special case to discuss. So when k equals 5, then we make again some very special choice. We fix the first 3 indices, 1, 2, and 3, and then we just take again consecutive indices. Again, a paired equation arises, which has infinitely many solutions in V. Again, there are infinitely many solutions for 5. And then when k is 6 or more, then what you do is practically that you consider k modulo 4. So you write k in this shape, a bit tricky shape, but practically it means that you consider k modulo 4. And then you say that, well, if k is divisible by 4, then you can just combine such quadruples, because you just make different choices of t, and then you have blocks of 4 indices, you can make them distinct, and that's it. What if k is say 1 mod 4? If k is 1 mod 4, then you take just one such quintuple, so 5 tuple, and many quadruples, and then you can get your k. What if k is 3 mod 4? Then you take just a triple, of course, and many quadruples, and then you get your k again. And what if k is 2 mod 4? This is a bit more tricky. Then you take one triple and one quintuple and sufficiently many quadruples. You can say that, hey, 3 plus 5 is 8. It is not 2 mod 4, it is 0 mod 4. Yes, you are right, of course. But the trick is here I can show you. Here is our choice for triple, here is our choice for quintuple, and C2 is the same. So in fact, it means that C2 can be left out, and then now you have not 8 but only 6 terms, which means that you are in the 2 mod 4 case, and then you are done also for these choices of K. Okay, so this means that we could prove that there are infinitely many solutions for K-term products of Catalan numbers being squares if K is at least 3. Okay, here we made a conjecture. There are also open problems later, you will see. So here you see in this construction we really put together things without paying attention what happens inside, and we think that in fact you can make you can choose k-tuples of different indices such that the product is a perfect square but no subproduct is a square. For any k you can do that. This is our conjecture. Because here we didn't pay attention about subproducts, so you can somehow, for any k, you can make some kind of independent product. So the indices are independent in the sense that no subproduct would be a square. For every k, you should be able to reach that. Well, this is what we think, but in this direction we practically have no results. Okay, let me continue with a related problem, still about squares, but now the situation is that we would like to start from one Catalan number and we would like to make it a square. In what sense? Well, you just start from fixed n, so you write a1, this is the starting index, and then you would like to find smaller indices such that this product is a square. So you start with some Catalan number, you take the product, you multiply it by smaller index Catalan numbers, and you would like to get a square. Well, this is just a kind of extension of a problem of Erdős and Graham for factorial. So they were interested just in this question. You start with n factorial, and you would like to make a square out of it by multiplying it by smaller factorials. Can you do that? How many terms you need, etc. So such questions were discussed by Erdős and Graham for factorials. So we took up this question for Catalan numbers. So we just defined P2 to be the set of those indices, those positive integers n, where for which n equals a1, and then for which you can find smaller indices such that this product is a square. So for what n you can reach it. And there are further questions, I will mention them at the end, but the main question, of course, that can you reach it for some n or not? Can you characterize those indices n for which you can do that? And well, it turns out that if n is at least 6, for the smaller cases are simple to look at, of course, but if n is at least 6 and 2n minus 1 is not a prime, then n can be, well, made a square in that sense that Cn can be multiplied by smaller index Catalan numbers to get a full square at the end. So the condition here is that 2n shouldn't be a prime. And well, I will also mention at the end, but I would like to point it out already here. What is the reason for that? I just go back to the definition of Catalan numbers. I promise that I will do that a few times. So what is a Catalan number? Well, product of positive integers from n plus 2 to 2n divided by n. Well, if 2n minus 1 would be a prime, 2n minus 1 is a prime. If you take a product of this Cn by a smaller index Catalan number, then the largest term will be only 2n minus 2. So 2n minus 1 is a prime, then Cn is hopeless. That prime will sit in the product forever at the first power. You cannot diminish that. So that's why we have this condition, and you cannot get rid of that. It is a natural condition. It must be there. 2n minus 1 cannot be a prime. Otherwise, no hope to make a square product starting with Cn in this way. but the nice property or nice phenomenon is that otherwise you can always reach a square in this way. And again, this is a simple argument, so I would like to show you how it works, only the sketch of the proof. A similar argument also works for factorials. So what you can do here is that, okay, so let's suppose that n is at least 6, 2n minus 1 is not a prime. And then there are two stages to make. The first stage is to reach a situation where the square free part of the product is at most 7. I mean, the largest prime in the square free part of the product is at most 7. So you start with n, you take smaller indices and you make a product, and you would like to have the square free part, this is denoted in this way, and the largest prime of the square free part should be at most 7. How can you do that? Well, in fact, it's very easy to reach it by an inductive inductive argument. You start out from n, a1 equals n. You write q1 for the largest prime in the square free part of this Catalan number of index a1. And then if q1 is at most 7, then you are done with the first stage. Otherwise, you just take and appropriate a2, which is smaller than, of course, a1, such that so you take in this way the second index, and then you can check easily that the greatest prime divisor of the square free part of this product will be strictly smaller than the original greatest prime was in this Catalan number. So you can decrease the greatest prime in the square free part by taking such a product. And then you just iterate this procedure. You can guarantee that q1 is at least 11 anyway, so this prime will be at least 11, otherwise you are done. And you can also guarantee that a2 is not too small, it is at least 6. And then you just iterate this process, and then at the end of this procedure you arrive really at a stage where you have indices, they are all at least 6, and the product has greatest prime divisor 7, I mean for the square free part. Okay, and then what? And then you are just have to consider the small cases. You just list the small Catalan numbers up to C5. So you know that you are down to index 6 in the worst case. So you didn't touch any number from this list. And then you just write out what these numbers are. And then you see they are 1 and 2 and 5 and 14. Well, this should be 2 times 7, sorry, not 2 times 6, of course. And then 2 times 3 times 7, 42, this is C5. And then the point is that you can just play along with these primes, and then you can really generate one prime from 2, 3, 5, and 7 on an odd exponent. So if you need in this product what you got so far, in this product, if you need to add, if you multiply with any small prime, you can just combine from this small list, and then altogether you will reach a square in this way. Okay, some remarks or some questions. So this works in a smooth way. Yes, but still there remains an interesting question, but just some remarks. I already mentioned this, that the 2n minus 1 is not a prime, this condition is necessary. You can ask that, what about higher powers? Why only squares? Why not cubes or higher powers? Well, we have an argument, a heuristic argument, which is based on some well-known facts related to distribution of prime numbers, that you cannot do this for higher powers. Of course, you need some natural condition about non-primeness of certain factors, but that will be not sufficient. But only a heuristic argument shows this. And an interesting question remains that, okay, this argument works, but you have no control in this procedure. We don't have any control on the number of terms you need to get a square out of Cn. how many terms do you need there? It would be very interesting to give an upper bound for the number of terms needed. For factorials, you can do that. But so Erdős and Graham could do that for factorials, but not for Catalan numbers. I mean, for Catalan numbers, we couldn't give an upper bound for this. Okay, so some interesting question remains. So let me turn to higher powers. Here I have fewer results to talk about, and here the proofs are more technical. So here I will just mention the background mostly. So the first thing is that, okay, now let's consider this equation. We would like to have products of Catalan numbers equal L's powers, and L can be now any positive integer, at least 2, of course. Can you do that? Well, here in this theorem, in the next theorem, we were interested in the number of solutions, the magnitude of solutions up to x. So our question was that, okay, can you do that many times? And then it turns out that you can do that really many times. So this product, the product of different Catalan numbers, can be an S powers in many cases. Okay, how to do that, how to measure that? Well, the statement is that if x is large enough, then this equation has so many solutions when the indices are really subject to change. So the indices are arbitrary, even k is arbitrary. So how many k tuples of Catalan numbers can you find up to x? The indices can run up to x, and k you can also choose freely, such that the product is an L's power. And what is this expression? Well, you see that this is not exponential, but almost, so kind of sub-exponential expression. Here is the dependence in L is just in this way. So sub-exponential. Of course, the number of tuples up to x would be roughly 2 power x, so an exponential expression. And in a sub-exponential number of cases, you really can get an L's power. So in many cases, you can get an L's power. And what is the reason of that? Well, the reason is, so here I just give some very brief explanation. It is a technical proof, but the reason is that Catalan numbers have small prime divisors. More precisely, if you consider Catalan numbers, so you consider CA, A is at most x, then it is very easy to see that the prime factors of this Catalan number is at most 2 times x. So somehow the prime factors are really rather dense. They are in a dense set. And somehow it means that then you will have a lot of collisions. So you will have a lot of cases when you can really play along with these prime exponents, and you will get L's powers. You can manage to do that. A bit more precisely, not much more precisely, a little bit more precisely, here we used a beautiful result of Alford, Granville, and Pomerance. It's a classical result. They used this, they developed this tool when they proved that there are infinitely many Carmichael numbers. So this is their result from a result of them from that paper. So what is it about? Well, if you consider the multiplicative group generated by a set of primes, okay, let's stick to our case, of course. So P is at most 2x, x is fixed. So consider the multiplicative group generated by these primes. Modulo S powers. What does it mean? Well, you just take the group generated by these primes, modulo S powers of the same primes, of course. And then you define ng in the following way. Let this be the smallest index n, such that any sequence of n consecutive elements in this group contains a subsequence with the product being the identity. Identity means S powers, of course. So n is the smallest index, such that if you take any n consecutive elements, then as a subsequence you will always find an S powers identity. Okay, and what is the magnitude of this ng? And what turns out that in our case this ng is, let me say, quite small. So you don't have to build too large sequences, too long sequences. You will always get a subsequence such that the product is identity. And this will give you S powers, and then you will get the statement. But here you require a lot of non-trivial argument. So a lot more non-trivial argument is needed here. It's not an immediate thing to get, but this is the main tool. Okay, and then finally, just about powerful numbers in products of Catalan numbers. So here we shall take. So here we take up only a special case. So we only took up a special case here. Namely, we take products of two Catalan numbers. You can say it is really special, but it will be even more special because we take two consecutive Catalan numbers. So, well, of course, powerful is much more general than power. So here we had to make some restrictions, and our restriction was this, that just product of two consecutive Catalan numbers. Can it be a powerful number or not? When it can be, how often it can be, things like that. Okay, so, well, what is a powerful number? Of course, you know this very well, but let's recall. A powerful number is just a positive integer, such that if p divides n, then also p squared divides n. In other words, every prime divisor of n occurs at least on power 2 or larger. Well, it is very easy to see that powerful numbers also always have such a representation. You can always write a powerful number as a product of a square and a cube. You just play along with the exponents, mod 2, mod 3, and you can really get it very easily. Okay, and then we have here two theorems. The first theorem is a kind of description of how powerful numbers, so how products of consecutive Catalan numbers look like when the product is a powerful number or not a powerful number. So how do they look like? And already this theorem indicates that, well, the product will be powerful quite often. But this is a kind of qualitative result. So it is kind of description, but we couldn't use it directly to get some quantitative statement. So what is this theorem about? So here we would like to describe products of consecutive Catalan numbers which are powerful. And this product is powerful if and only if m, so this first index, is not of this shape. Roughly speaking, this theorem says that this product is many times powerful. The reason is that the exceptional set, when this is not, this doesn't happen, is rather special. So what are the exceptional indices when the product is not powerful? Well, m equals 1 and 2. Okay. And then there is a small distinction between the primes 3 and larger primes. So if the product is not powerful, then m should be of this shape if you expand m in the number system base 3. So you expand m in base 3, then the digits should be very, very special. So you see that B0 is 0 and B1 is 1 and 2. Sorry, B2 is 0, B1 is 1 and 2, and B0 is 1. So some special choices. But the point is here that BI is 0 or 1. So no digit 2, roughly speaking, no digit 2 is allowed. Very serious restriction. Or it also can happen that m is of this, M also shouldn't be of this shape, if I put it in that way, to avoid if the product is powerful if and only if M is not of these shapes. So M also shouldn't be of this shape. You expand it periodically for some prime P. And again, I just show you the main restriction, where it is. It is here, BI should be small, should be in the first half of the digits. So only those cases are excluded. So only those M's are excluded which have some very special shape in some number system. So you can think that, okay, it means that at least many M's remain, for which you have a powerful product. How to prove this theorem? Well, I just mentioned that the main tool here was a classical theorem of Kummer on the exponents of primes in binomial coefficients. So Catalan numbers come from binomial coefficients. A small disturbance is made, so you can really use results concerning binomial coefficients. And here, this classical result of Kummer was really very useful and very strong tool. Okay, and then finally, so this is my last theorem. Okay, so we could give some kind of qualitative description of products of consecutive Catalan numbers not yielding powerful numbers, but still it was not sufficient to exhibit infinitely many cases even. And here there is a statement which says that, as one would expect, there are infinitely many pairs of consecutive Catalan numbers whose product is a powerful number. How to prove it? Well, it is rather simple proof. You just take this product, and then you see that here you have a full square. So if the first part is of this special shape, 7 power 3 times b squared, then you know that the product will be powerful. So only you should find infinitely many m's such that this equation holds. But this is a paired equation, and you can show easily that it has infinitely many solutions. So this is really just a special family, which really explicitly shows that there are infinitely many products of consecutive Catalan numbers being powerful. But an important problem remains. What is the order of magnitude of this set? So, okay, so can you tell that for how many indices m this product will be powerful if m goes up to x? And we cannot tell that. So here we were not able to give an answer here. Our calculations show that this set is quite large in some sense. This set should be the cardinality of this set should be around the logarithm of x. So we have some numerical results which support that, okay, this should be log x. So in many cases, you should really get a powerful number. Well, that's it. This is what I wanted to tell. Thank you very much for your attention.
Any question, please? Question from participants? ठीक है.
Hello. Yes.
Hello.
So, hello, sir.
Hello.
Can you hear me?
Yes, I can hear you. Yes.
Okay. So, Catalan number is a special case of recurrent sequence with polynomial coefficients, right?
You mean this? this case, so when we have 4 terms, am I too
No,
fast? No, here. Do you mean this?
I'm talking about the recurrence relation. This satisfy this by these Catalan numbers.
So, please repeat. So Catalan numbers and
Catalan numbers satisfy this recurrence relation with a polynomial coefficients, right? Because C
oh
n
yes,
plus.
yes, yes. Oh yes, oh, yes, yes, yes. I see. Yes,
Okay, so the
yes,
question
yes,
is,
yes.
if I take a general recurrence sequence with polynomial coefficients, is there any result
Yes.
related to powerful numbers or square in that direction?
Well, in general, it can be a difficult question, I think. So here it was really a special situation in the sense that, okay, we have really such a recurrence relation, but Catalan numbers are really very closely related to binomial coefficients, central binomial coefficients. So this means that their properties are really, at least in a large part, are close or are inherited from those of factorials, binomial coefficients. So we really have a lot of extra tools. So you see, a Catalan number, roughly speaking, is almost a central binomial coefficient. Only a small disturbance is there.
Okay,
So if you introduce large degree polynomials here, then probably it will kind of ruin the structure. So then it will be more difficult. This is my impression.
okay. Thank you.
You are welcome.
So there is one question in the chat box.
Yes, please.
There is one question in the chat box.
In the chat box. Oh, I see.
Yes,
I
sir.
check it.
Yes.
Yes. So the question is that can we study the power values of sum of Catalan numbers instead of product of Catalan numbers? Well, it is a very interesting question, definitely. So I like this question. But what I'm sure is it will be more difficult, much more difficult than the product of Catalan numbers. So the reason is something like yes. So here, if so once again I can tell that here we have factorials ultimately. And if you take products of Catalan numbers, then you talk about products of factorials, products of binomial coefficients with a small disturbance. And if you talk about products, then of course you are rather close to squares. Then products and squares, they are really very strongly related. When you say sums of such expressions, then it will be much more difficult. Maybe if you take sums of, say, consecutive Catalan numbers, for example, you just take two consecutive Catalan numbers and their sum. Then, of course, you just have Cn and Cn plus 1, and then you can take out the Cn from the sum, and then you see that a large part is just Cn. A large part is still very well structured. So if you take sums of Catalan numbers such that the indices are really close to each other, then probably you can prove related theorems or similar theorems. But if you say that you just take two arbitrary Catalan numbers which are very far away, then I don't see how to get control on the prime factors. So then you lose this control what is there for products. So maybe I could say that if you take close indices, then probably you can prove something for sums. And the indices are getting far apart, the situation is getting much more difficult. So this is what I think.
Thank you, sir.
You are
Thank you for
welcome.
your talk.
Thank you very much.
Hello, Professor
Yes.
Hajdu. Yeah, thank you so much. I will contact you later. Thank you so much.
Thank you. Thank you very much. Thank you very much. Have a nice conference. Thank you very much. Okay, so thank you very much. Have a nice conference. Goodbye.
এই মাইকের অফ কর, এই মাইকের অফ কর, মাইক অন আছে। Take the touch, take the touch.
I request the Jawan man from nature to share. So thank you very much. And our next speaker is Professor Panda from NSNTLA Rourkela. And the title of his talk is Ramanujan, Mahalanobis, and the House Indian. So thank you very much. It is a great pleasure for me to deliver a talk to my current institute. And actually, this occasion, I am getting this occasion for the second time. Actually, we are only reading from our one of our service here. So we are only listening to ourselves. So it is a great moment for me to speak something in front of myself. Story relating to Ramanujan and Mahalanobis. As you know, both of them are great in their area. Commonly studied in UK. And both of them in their 20s, both have genius. They will study the research paper story about them. The man who knew in rubber and here in one of the so the popular physics magazine trend it used to publish certain and that is in December
1913. And Sunday morning, one of these was sitting in with a copy of the book. Titled Ramananda Shruti. One is that President had a problem and what was the so what is the problem? I was talking several brothers with other builders, whether they were in Hungary. So the other place he said, he used to visit a Belgian friend there. He said, his house, the house of his friend was in a long street. Number on this side, 1, 2, 3, and so on. The number of houses on one side of his house had exactly same to the numbers of houses on the other side. He also said that he knew there were more than 50 houses on that side of the street, but not so many as 500. The tenth house number and how many houses are there in that street. So this K tenth house number. So when we the tenth house number is 204 and total number of houses in the street is 288. But Rama said and that give and step all the solutions of this problem, which is possible house number and last. So what is that? So if any the number of brothers friends house and any the number of houses in the street, then we need to solve this equation 1 plus 4 n minus 1 is equal to n plus 1 plus n plus 12. And our condition is 50 less than n is less than 500. So this is related to the problem of triangular number. As you know, the triangular number is a figure number. Already described in the figure. And the triangular number here is given by the sum 1 plus 2 of 12 is n into n plus 1 by 2. These are some properties of triangular numbers. A natural number is triangular number is 8 plus 1 square. The sum of two consecutive triangular numbers is square. It is a triangular number, the 19 plus 1 is also a triangular number. This is the figure. And some triangular numbers are squares, like D1 is 1, K is 39, T 39, 25. So how to find how to find all of the square to this property? N square is n plus 1 by 4. How to find all of them? And n square is you know is sum of two triangular numbers. Tn minus 1 plus t is equal to n square. And tn is n minus 1 by 2. So if we arrange it, tn minus 1 plus tn minus 1 is 1 plus 2 tn minus 1 and from tn, if we remove tn, it will be n plus 1 plus n plus 2. From the left hand side, we will get only tn minus 1. In the right hand side, tn minus tn. Tn. So, sum of n numbers and sum of n numbers. N plus 1, 2. So, if we have natural numbers x and r, let's try this equation 1 plus 2 x minus 1 plus x plus r is called the balancing numbers balance r. Of course, I am not going to details of balancing numbers. And our problem is to find how much the part x square is n into n plus 1 by 2 equal to 8x square plus 1 is square and y is 2n plus 1 plus 1 or 2 into x plus 1 and the equation of 8x plus 1 is y square and x equation y square and 8x square is equal to 1. It can be factorized in Z2 as y plus 8x is 1, y plus 8x is 1 and the first solution with positive probability x is 1 would not be 1. So if you find all elements of left rotate of not 1, then we can determine the value of all values of x. So C plus rotating the n is therefore yn plus rotate x, and C plus rotate is a unit. So C plus rotating the n is also a unit in z rotate. And we can find xn and yn as follows. This is very easy. So these are the values of xn and yn. And if we take alpha as 3 plus rotate and alpha 1 as 3 minus rotate, then we can see that alpha to the power n plus 1 is 6 alpha to the power n minus alpha to the power n minus 1. Similarly, beta to the power n plus 1 is 6 beta to the power n minus beta to the power n minus 1. And if we combine these things, we can easily see that xn plus 1 is 6xn minus xn minus 1. Yn plus 1 is 6yn minus yn minus 1. So x2 is x1 is 1, x2 is 6. Similarly, y1 is 3, y2 is 17. In this way, we can count the to 04 etc. And 2 times the last house number plus 1 appears in the numerator as y values. So possibly that was the control function. What another thinking, I don't know exactly, but I think this is the possible control function. This one. No. कस्टमर बैक नहीं गई Now, the question is, what happens if the sum up to the friends house number, not excluding friends house number, is equal to other houses in the street? So in this case, our equation will be 1 plus 2 of 12, where n is the friends house number, is equal to n plus 1 plus n plus 2 of 12, m is the last house number. And in this case, we can write this equation as n into n plus 1 as m into n plus 1 by 2. So the right hand side is a triangular number, but left hand side is not a square. It is a chronic number or called oblong number. And if we multiply 4 and add 1 to both sides, we will be left with 12 plus 1 whole square is 12 square plus 12. So if we again multiply left hand side by 2, then we will be left with an equation 2 into 2n plus 1 whole square is 2n plus 1 whole square minus 1. So if we let x is 12 plus 1, y is 2n plus 1, then we are left with the equation y square is 2x square plus 1. So again, by similar approximation, for large value of x, y by x will be approximately equal to root 2. But we should keep in mind that both y and x are odd in this case. Now we expand root 2 as a continuous fraction. So what we have to do? Root 2 is equal to 1 plus root 2 minus 1. So it is 1 by 1 plus root 2. And everywhere we have to replace root 2 as 1 plus 1 by 1 plus 1 by 1 plus root 2. If we go and replace it, we will get a continuous fraction. First term is 1. All the remaining terms are 2. Back. K1 is 1. K2 is 3 by 2. So we have to discard K2, K4, etc. because here the numerator and denominator both are not odd. Y and x has to be odd. Then K3 is 7 by 5. In this case, both the terms are odd. K4 is 17 by 12. We have to discard. K5 is 41 by 29. These are the convergents. So, whenever both numerator and denominators are not odd, we have to discard them. Only in case of K1, K3, K5, K7, both numerators and denominators are odd. So, our x1 is 1, x2 is 5, x3 is 29. Is 2 into last friend's house number plus 1, then friend's house number is 13 and last house number 2 into 20 plus 1. So 20 is the last house number, so last house number is 20. So this is about the Taxicab number, actually known to everybody. I don't want to waste time here. Thank you. Any question? Sir. Sir, it's there, sir. Yeah. This one. Yeah, it is very tall. Yeah, 1729. Yeah, 1729. Oh, 1729, sir. Not 100. Error, sir. This is the smallest number. student sum up two positive cubes in two different ways. Yes, sir. Sir? Sir, it can be very much. Sir, it can repeat because they test numbers between 1 to 12 only. It's very simple to verify. Yeah. No, we have to deal with numbers from 1 to 12 only. So if you take every pair even, there will be 12 C2 pairs. So it will be very easy to verify. 12 C2 pairs will be there. 11, 66 pairs will be there. Even if you verify everything. Direct verification or crude verification. So there will be 66 pairs of number and one can easily verify. That these are the two possibilities. Okay. Combinatorial actually we have not got any combinatorial interpretation, but you can express it.
That is incomplete balancing number.
Yeah, but in balancing number directly there is no such thing, but you can express it as some combination, sum of some combination. Yeah. But there is no, for direct balancing number there is no such interpretation. For complete balancing number, yeah. Okay.
It is Lie algebra. Okay. And actually it is a true algebra, it is not a lie algebra. The Lie algebra concept comes like that, it came into existence like that. You must have heard about Galois theory. What is Galois theory? Galois group, that is your suppose I want to solve a linear equation, I can solve it very easily. Suppose I want to solve a quadratic algebraic equation, I can solve it. If it is a cubic equation, still I can solve it. But if you go into an higher order algebraic equation, it is not so easy to solve a higher order algebraic equation or a simultaneous algebraic equation. So there is he tried to generalize this Galois concept into solving higher order differential equation or higher order simultaneous differential equation. And while developing this theory parallel to your Galois theory, he found out that the symmetry of the solution of these differential equations have also obeys some symmetry. And this symmetry actually gives rise to a group. What we have learned in your first year of teaching in mathematics, that satisfies group. And that group is slightly different from your group what we have learned. Group what we have learned is called a discrete group. But this group is somewhat that we may call a continuous group. Algebra, how it is a vector space. It is nothing but a vector space, but with some extra bilinear operation that is called link bracket. That's all. That will be the end of my talk. But before that, I want to tell you why it is necessary. So I shall start with the practical day-to-day life problem. It happened actually 5 days back. I am not telling truth, but I am bluffing you. Just 5 days back, I came to Sambalpur near city railway station, and I saw that there was a marriage party. I was invited, of course, and there was a very narrow road. So I bought a new car. But I don't drive. I don't know the driving much. But I happily came from Rourkela to Sambalpur. But I saw that in the marriage reception, what happened? There was a very narrow road, and in the narrow road, the car number one was parked here. Then I saw there is another car also, C2. It was parked like that one, and I thought there are many empty spaces, so I parked my car here. This is my car. And I thought now I can drive backward my car and I can go out of the road and I can go to Rourkela back. But while coming from this marriage reception, I saw that behind this car there is another car. Behind that is another car. And I cannot take out my car. How I shall? Because the engine here. This is my engine here. I was going only traveling. Little gap, of course, was there. So I can drive forward or I can drive backward a little, not much. So how do we move the car? So I thought, let us apply some mathematics behind this one, so that I have learned Lie algebra, Lie super algebra, and many big sort. So why not? I thought that Lie algebra will help me in coming out from this problem. So what I did, I went to the, I learned that how to deal with this Lie algebra. How Lie algebra will help me in moving the car from here. Then I thought, if Lie algebra I am studying, what is the background for this one? Lie group. Lie group. What is a Lie group? As I told you, it is a differentiable manifold. It is a differentiable manifold. So I thought that this space on which I am here, this may describe a manifold. And that manifold may be a differentiable manifold or may not be differentiable manifold. So let us take a chance. S1 into S2. So this will be a manifold R2, S1 and S2. And so this is a manifold, and of course I am not going to prove this one that this is a differentiable manifold. I knew it is a differentiable manifold, and I have to check it whether it forms a group or not. So I have some operation, something like your drive. Theory you have studied. Again, I am going back to group actually. What is a group? Group everybody knows. Then I know you must have heard about matrix group. Matrix group also, like what are the matrix group? GLNR or GLNC or GLNF you can write down. All invertible n cross n matrices or not. So they form a group under matrix multiplication. So GLNF is also a matrix group, but there is another concept. That is the concept called your symmetry. D group. That is my thought. And on that basis, I shall solve that problem. So what is your symmetry? Symmetry, you know how symmetry, being all the mathematics student, everybody knows how symmetry gives rise to a group. You have studied examples of a group, like the symmetry of a equilateral triangle. Symmetry of a equilateral triangle. What is the symmetry means? It means under some operation of these matrices, if the geometrical shape of the equilateral triangle remains same, then that will be a symmetry operation. So what is the symmetry operation? Symmetry operation is, you don't change anything. These vertices 1, 2, 3, you don't change. That will be one element. Then you change by 120 degree anti-clockwise. That will be another element. You can change 240 degree anti-clockwise, another element. And if you again 360 degree, again anti-element, that will be another element. And also, if you consider an axis which passes through 1 and along the plane of the triangle, then reflection of this one 3 will come to here, 2 will come to here, but the geometrical shape of the equilateral triangle remains constant. So that will be another reflection about one axis. That will, then similarly reflection about two axes. Then similarly reflection about the vertices 3, not 3 axes, vertices 3. So 1, 2, 3, 4, 5, 6. So these 6 elements form a group. And you know what is this group called? You know what is a dihedral group. So dihedral group with 3 vertices, now these 6 are actually D to H. So if it is equilateral triangle, if it is a square, D8. Similarly for a hexagon, D12. You go on like that one. So this gives rise to a group. So anything there is symmetry operation, and on the symmetry operation, if the geometrical shape of the object remains constant, then it gives rise to a group. You can prove this one. This will satisfy anti-element, associativity property, closure property, all will be satisfied. So this forms a group. And these elements are 1, 2, 3, 4, 5, 6. So this, you can count this one. So this is a discrete group. But suppose now I generalize this one into a hexagon, or number of vertices of n polygon is now, so it will give rise to dihedral group. And now you change increase the number of n's. So when you increase the number of n's, what will happen? What structure you will get? This is 3 vertices, 4 vertices, 6 vertices, then n vertices. Now n becomes go and increase and increase. What will happen? What structure you will get? A circle. You will get a circle. You will get a circle. So when n increases to a very large number, then it becomes a circle. So now tell me, what is the symmetry of the circle? Like your symmetry of the triangle, symmetry of the equilateral, square, or symmetry of the hexagon you have studied, it gives rise to a dihedral group. So what is the symmetry of this circle? What is the symmetry of the circle? I can write down symmetry of the circle. Suppose I move into anti-clockwise direction. So initially I have coordinate x and y. But now after some rotation by an angle theta, the new position will be x prime and y prime. I know the relationship between x prime, y prime and x and y. What is the relation? What is the relation? X prime is equal to x cos theta. Y prime is equal to minus x sin theta plus y cos theta. This is the relation I have. This relation I know. And what is this? In the matrix form, how do you write down? X prime, y prime is equal to cos theta, sin theta, minus sin theta, cos theta, and this is my x and y. So this is your x prime, y prime. So now you see, now if I denote this to be a vector, so I write down x prime is equal to, this is my old position, old vector, and this is my a matrix. So I write down this matrix as A theta. So what is this aspect? There is some original vector, some operator acts on this vector, it gives rise to a new vector. So now this set of operators A theta, you will see this gives what is constant along this one. In this geometrical shape, x prime square plus y prime square is equal to x square plus y square, which they both are equal to the radius of the circle. So when this remains constant, then this will form a group. Because I told you, symmetry tells me that if there is change in the coordinate system and some property of the system remains constant, then it gives rise to a group. So this in two dimensions. So consider this will be a special orthogonal group of S of theta. So this group is actually a differentiable. This group. So these are the continuous SO2, SO3. I have visualized the symmetry of a circle. There can be many things. For example, I told you a set of operators. Suppose V is a vector space. Set of to X and Y. And two important bilinear form I know. One is your symmetry xy is equal to yx, and another one I know have xy is equal to minus of yx. So basis on this bilinear form, the subset of operators will form a group that will give rise to a actually called social orthogonal group, one set. And another set, this will give rise to, this is actually acting 2n dimensional space, even dimensional space. So that will give to the symplectic group. So I have social orthogonal group, I have social symplectic group. So this type of groups are actually Lie groups. And this Lie, now you see what is the difference between the ordinary group and Lie group? Here these elements lie on a continuous many. In contrast to a discrete group, what we have now. So just now I am going to tell you how to obtain the Lie algebra from this Lie group. One point is that I have told you a Lie group is a differentiable manifold. Okay, it is a differentiable manifold with group properties. If it is a group properties, then it must have some identity element. So, suppose this is my Lie group manifold, and at this point, this is my identity element 1. Okay, here I forgot to tell you this SO2. SO2, what it is represented by? The matrices something like A theta, cos theta, sin theta, minus sin theta, cos theta. So, you can generate all the elements of the group by changing the value of theta. By changing the value of theta, you can find out all the elements of the group. So, this is called actually a one parameter Lie group. One parameter Lie group. There can be two parameter Lie group or in general n parameter Lie group. But SO2 is a one parameter Lie group. So in this basis, what I told, now suppose this is my Lie group, this is my differentiable manifold, and it is a Lie group, so it is a identity element. So what I shall do, now I shall consider on this manifold a curve. I shall consider a curve which passes through this identity element. I consider a curve which passes through identity element. So this curve is actually a one parameter subgroup of this Lie group. This curve is represented by one parameter subgroup, and it passes through the element. So, and it satisfies a property called A or A0, which is equal to 1. Suppose I calculate my T is equal to 0 here. So, it is A0 is equal to 1. Similarly, I consider another curve. I consider another curve also which passes through this identity element. So, suppose this is your AT, this is another one parameter subgroup, and BT, but it also satisfies the same property. BT is equal to, BT, and with B0 is equal to, again it passes through the identity element. Now what I will do, I shall draw a tangent to this curve at this point. So I draw a tangent to this curve at this point. So when I draw a tangent to this curve at this point, so what value I will get? I shall tangent with dAt, so I shall differentiate with respect to t at t is equal to 0. So I shall draw the tangent, so that tangent, that will be a vector, so let that vector be represented by m. This vector is represented by m. And similarly, I shall draw another tangent to this curve bt at this point. So this will be again be a vector, but this vector will be dv by dt. So I shall obtain another vector m. Now what I told you, I have told you this vector at is a group element, this vector bt is a group element. And I know that there is in group, you have studied, what do you mean by group commutator? What is group commutator? Of two elements. It is something like your the group commutator between two elements will be A, B, A inverse, B inverse. And if this is the group commutator, now you see this is group element, group element, group element, group element. The operation between these are group operation. So this is also a group. This is also a group element. So let that group element be your C. Let that group element be your CT. You will see that this CT will also pass through the anti-element. The CT will pass through also the where this is equal to this one. Now what I will do? I said I want to find out tangent to this, tangent to this curve at this point. It will be another vector. So let that vector be, suppose your L. L means dct by dt at t is equal to 0. dct t is equal to 0. So this will be another vector. So this vector is equal to L. But when you will see that I have to differentiate this one dct by dt at t is equal to 0. I have to define t by dt at t is equal to 0. I have to find out. When I shall find out, I shall see that for matrix Lie group, I have told you matrix Lie group for a GL NR or GL NC or SL NR or SL NC, all the matrix group, this will be equal to, I shall find out the calculation and little algebraic manipulation, I shall get this value to be Mn minus n. This will be your Mn minus n. That is, I denote this one as Mn. That is Lie bracket between the two vector fields M and N. This is called Lie bracket between the two vector fields M and N. So what I have done? Now consider this is a curve, tangent vector, this is a curve, tangent vector, this is a curve, tangent vector. So consider all the curve which passes through the anti-element and draw the tangent. So what you will obtain? You will obtain a tangent plane. So that tangent plane is nothing but a vector space. All the tangent vectors on this plane will also satisfy the properties of the vector space. So particularly this tangent space is a vector space which obeys also this condition. This is equal to L. Some extra bracket. When there are two vectors on the tangent space, the Lie bracket between the two vectors will also give rise to a new vector. So what is this Lie? Actually, this is your Lie algebra. What is the Lie algebra? Lie algebra is nothing but the tangent space to the group manifold at the point at the identity. And the definition of Lie algebra tells me that so L is a vector space and it is over certain extra bilinear operation called Lie bracket which takes L cross L to L. L cross L to L. And it obeys certain property. What are the property? What property is that it is bilinear? Suppose x, y belongs to L, then x and y is equal to minus of yx. Then it is linear in first entry, linear in second entry, so it is called bilinear. So one relation I am writing alpha x plus beta y z equal to alpha that is z plus beta y. And also similarly for the second entry. And the third one is that it satisfies Jacobi identity x y z plus y z x plus x sorry x y z y z x x y z x उसके बाद z x is equal to. This is called your Jacobi identity. This is my Jacobi identity. So this is the definition of the Lie algebra. And vector space has to be either over a field, and you know that field can be real, if field can be complex, or field can be quaternion, or field can be anything. So if it is over real number, then it is called a real Lie algebra. If it is complex number, then it is called a complex Lie algebra. So it is simply a Lie bracket which satisfies this problem. So now within only 2 minutes you should answer me. You have studied from your +2 onwards. You have studied Lie algebra. So give me the simplest example what you have studied in your +2 onwards. The example of a Lie algebra. You consider a vector space. You consider a extra bilinear operation. An extra bilinear operation satisfying this property.
Continuous function.
Anyone? R3 you have studied. And R3 you will study in your class product. This is a Lie algebra. This is a Lie algebra. Because this curve, I know that x cross y is equal to minus y cross x. I know that x cross y cross z is equal to y cross z cross x plus z cross x plus y is equal to 0. You know, like this one. So this is your simple algebra. R3x. So, just one part. Let me finish this one. Don't ask me difficult questions. So now this is LM. Now I am telling you how this definition of the Lie algebra will help me to come out from this one. It actually will help me. How? I am not an expert driver. Expert driver, if you take a expert driver to this place, he will bring the car out in this direction. He will bring the car in this direction. But I don't have experience, so I have to do something. I said I have to use mathematics. So what is my mathematics? Now I know that this is a group manifold, something like your R2, S1, S1. So I have a corresponding Lie algebra over that one. And I know the two operations, drive and steer. Those are the group elements actually. You can prove that one. So these are the group elements, drive and steer. So what I will do, I shall make use of group commutator. So ds, d inverse, s inverse, and I shall do this type of calculation. If I do this type of calculation, then what I will get? I will get the corresponding from the group drive algebra element, and here the steer element. So I shall obtain something like your ds Lie bracket. I shall get ds Lie bracket. This ds drive and steer Lie bracket will give me a mathematical expression actually. It can be calculated. Actually, I have not given you mathematical expression. This is x prime, y prime, theta prime, phi prime, and this is equal to this one plus x, y, theta, phi. Here you will get like that mathematical expression. And from this I will drive and steer. This will give you a mathematical expression. You will closely check. This will be rotation. This will be a rotation. So if it is a rotation, it is with the help of the drive and steer, I do the rotation. But here I cannot do the rotation because there is no enough space. If enough space would have been, I have rotated and I would have come back. But there is no rotation. So what I will do, I shall take another Lie bracket. That is drive, this rotation R. When I make this Lie bracket drive and rotation, this one, I shall get a mathematical expression which will give me another vector field that is called your slide. That is called your slide. So what is slide? Slide means it can slide exactly in this direction. But how to obtain this slide? This slide can be obtained by, you see, dr is slide, then ds is equal to slide. Now but how this d by ds is obtained? From the t is equal to 0 by group commutator. Then I can take another group commutator. So with the help of this drive and slide, drive and steer, drive and steer, a do of group commutator, and you will see that the expert driver does also this one. Only through little drive forward, drive backward, D and D inward, steering clockwise, anti-clockwise, suppose positive, then anti-clockwise it is negative. So he will do a lot of manipulation, and you will see that the car will automatically will come. So that is actually
এটা বলবেন না হইতে পারে এটা কোনো রাইজ বলা
চালানো আর খাবে নেই কালকে খাবো না কালকে আজই নি খাওয়ানো pasok gaganda gaganda na po
भाई बहन दी सेवा नहीं नेशनल का भाई बहन दी सेवा नहीं but now it is
45 minutes impossible কথা নাই করা ভাই और देखा ए साइड साइड क्लियर साइड क्लियर साइड
अरे मग बॅग का सेट चला आयुष मग बॅग का वाटते आयुष पचार ब्लू कलरটা ওটা কাম করো ওটা কাম করো আমরা ভিডিও চালাবো
a place where knowledge meets tradition, and aspirations turn into achievements. As we move forward through this lush green campus, we approach a hub of mathematical excellence, our Department of Mathematics. Established in 1969, the Department of Mathematics has been a pillar of academic strength, shaping young minds and advancing the frontiers of mathematical research. Step inside, where equations come to life, numbers tell stories, and every theorem unravels a new possibility. Welcome to the Department of Mathematics, Sambalpur University, a place where numbers speak, equations solve mysteries, and legacies are built. For decades, this department has been guided by brilliant minds, professors whose dedication and passion for mathematics have shaped generations of scholars. Here, we honor those who have dedicated their lives to mathematical excellence. From esteemed educators who have shaped the department to scholars making groundbreaking contributions in the field, this board is a testament to their impact. Their work continues to inspire, their teachings remain immortal, and their legacy lights the path for the mathematicians of tomorrow. Every name here tells a story of perseverance, discovery, and an undying love for mathematics. This board is more than just a collection of photographs. It evolves. Beyond research and teaching, the smooth operation of the department relies on this office, the center of all official activities, from admissions to academic records and student services. Every aspiring mathematician's journey at Sambalpur University begins here. From admission processing to course registrations, scholarship applications, and academic certifications, this office ensures a seamless experience for students and faculty alike. With dedication and efficiency, the administrative team works tirelessly to support students, helping them navigate the path of higher education in mathematics. But mathematics is more than just formulas and theorems, it is also about ideas, creativity, and expression. And here, at our wall magazine, students showcase their mathematical explorations, artistic insights, and academic reflections. This platform provides a space for students to share their thoughts, discoveries, and even the beauty of mathematics beyond the classroom. Whether through articles, puzzles, or artwork, every piece here reflects the passion and curiosity of young minds. Learning happens not just in classrooms but also through discussions, creativity, and exploration. The Wall magazine stands as a testament to the lively mathematical culture of our department. At the helm of our department stands a leader dedicated to academic excellence, Professor Arun Kumar Tripathi, our esteemed head of the department. Guiding both faculty and students, Professor Tripathi ensures the smooth functioning of the department while fostering an environment of research, learning, and innovation. With a vision for progress and a commitment to excellence, our head of the department leads the department toward new academic horizons, ensuring that the legacy of mathematics at Sambalpur University continues to grow. But some teachers, even after retirement, continue to guide and inspire students. Here, we meet Professor Sabita Sahu, a renowned expert in algebra, who, despite retiring, remains deeply connected to the department. A passionate mathematician and a dedicated teacher, Professor Sabita Sahu has shaped the lives of countless students. Her expertise in algebra continues to enlighten young minds, proving that true educators never stop teaching. Her commitment to mathematics goes beyond retirement. Whether through lectures, research discussions, or mentoring students, Professor Sahu's presence in the department remains invaluable. Great teachers never truly retire, they continue to guide, inspire, and shape young minds. As we move ahead, we come to the heart of student interaction, where young minds receive mentorship, encouragement, and expert guidance from our esteemed guest faculties. Here, we meet Dr. Madhuchanda Sahu and Mr. Rajesh Kumar Sahu, two dedicated faculty members who not only excel in their respective fields but also connect deeply with students as mentors and guides. It was a quiet afternoon in the Department of Mathematics at Sambalpur University. The sun cast long shadows through the trees outside, and a gentle breeze carried the distant echoes of students engaged in lively discussions. Amidst this academic serenity lay the heart of the department's digital realm, the computer lab. In the mathematics department's computer lab, students and researchers work with latex to draft research papers, project reports, and presentations. Welcome to Sambalpur University, a place where knowledge meets tradition, and aspirations turn into achievements. As we move forward through this lush green campus, we approach a hub of mathematical excellence, our Department of Mathematics. Established in 1969, the Department of Mathematics has been a pillar of academic strength, shaping young minds and advancing the frontiers of mathematical research. Step inside, where equations come to life, numbers tell stories, and every theorem unravels a new possibility. Welcome to the Department of Mathematics, Sambalpur University, a place where numbers speak, equations solve mysteries, and legacies are built. For decades, this department has been guided by brilliant minds, professors whose dedication and passion for mathematics have shaped generations of scholars. Here, we honor those who have dedicated their lives to mathematical excellence. From esteemed educators who have shaped the department to scholars making groundbreaking contributions in the field, this board is a testament to their impact. Their work continues to inspire, their teachings remain immortal, and their legacy lights the path for the mathematicians of tomorrow. Every name here tells a story of perseverance, discovery, and an undying love for mathematics. This board is more than just a collection of photographs. It evolves. Beyond research and teaching, the smooth operation of the department relies on this office, the center of all official activities, from admissions to academic records and student services. Every aspiring mathematician's journey at Sambalpur University begins here. From admission processing to course registrations, scholarship applications, and academic certifications, this office ensures a seamless experience for students and faculty alike. With dedication and efficiency, the administrative team works tirelessly to support students, helping them navigate the path of higher education in mathematics. But mathematics is more than just formulas and theorems, it is also about ideas, creativity, and expression. And here, at our wall magazine, students showcase their mathematical explorations, artistic insights, and academic reflections. This platform provides a space for students to share their thoughts, discoveries, and even the beauty of mathematics beyond the classroom. Whether through articles, puzzles, or artwork, every piece here reflects the passion and curiosity of young minds. Learning happens not just in classrooms but also through discussions, creativity, and exploration. The Wall magazine stands as a testament to the lively mathematical culture of our department. At the helm of our department stands a leader dedicated to academic excellence, Professor Arun Kumar Tripathi, our esteemed head of the department. Guiding both faculty and students, Professor Tripathi ensures the smooth functioning of the department while fostering an environment of research, learning, and innovation. With a vision for progress and a commitment to excellence, our head of the department leads the department toward new academic horizons, ensuring that the legacy of mathematics at Sambalpur University continues to grow. But some teachers, even after retirement, continue to guide and inspire students. Here, we meet Professor Sabita Sahu, a renowned expert in algebra, who, despite retiring, remains deeply connected to the department. A passionate mathematician and a dedicated teacher, Professor Sabita Sahu has shaped the lives of countless students. Her expertise in algebra continues to enlighten young minds, proving that true educators never stop teaching. Her commitment to mathematics goes beyond retirement. Whether through lectures, research discussions, or mentoring students, Professor Sahu's presence in the department remains invaluable. Great teachers never truly retire, they continue to guide, inspire, and shape young minds. As we move ahead, we come to the heart of student interaction, where young minds receive mentorship, encouragement, and expert guidance from our esteemed guest faculties. Here, we meet Dr. Madhuchanda Sahu and Mr. Rajesh Kumar Sahu, two dedicated faculty members who not only excel in their respective fields but also connect deeply with students as mentors and guides. It was a quiet afternoon in the Department of Mathematics at Sambalpur University. The sun cast long shadows through the trees outside, and a gentle breeze carried the distant echoes of students engaged in lively discussions. Amidst this academic serenity lay the heart of the department's digital realm, the computer lab. In the mathematics department's computer lab, students and researchers work with latex to draft research papers, project reports, and presentations. Welcome to Sambalpur University, a place where knowledge meets tradition, and aspirations turn into achievements. As we move forward through this lush green campus, we approach a hub of mathematical excellence, our Department of Mathematics. Established in 1969, the Department of Mathematics has been a pillar of academic strength, shaping young minds and advancing the frontiers of mathematical research. Step inside, where equations come to life, numbers tell stories, and every theorem unravels a new possibility. Welcome to the Department of Mathematics, Sambalpur University, a place where numbers speak, equations solve mysteries, and legacies are built. For decades, this department has been guided by brilliant minds, professors whose dedication and passion for mathematics have shaped generations of scholars. Here, we honor those who have dedicated their lives to mathematical excellence. From esteemed educators who have shaped the department to scholars making groundbreaking contributions in the field, this board is a testament to their impact. Their work continues to inspire, their teachings remain immortal, and their legacy lights the path for the mathematicians of tomorrow. Every name here tells a story of perseverance, discovery, and an undying love for mathematics. This board is more than just a collection of photographs. It evolves. Beyond research and teaching, the smooth operation of the department relies on this office, the center of all official activities, from admissions to academic records and student services. Every aspiring mathematician's journey at Sambalpur University begins here. From admission processing to course registrations, scholarship applications, and academic certifications, this office ensures a seamless experience for students and faculty alike. With dedication and efficiency, the administrative team works tirelessly to support students, helping them navigate the path of higher education in mathematics. But mathematics is more than just formulas and theorems, it is also about ideas, creativity, and expression. And here, at our wall magazine, students showcase their mathematical explorations, artistic insights, and academic reflections. This platform provides a space for students to share their thoughts, discoveries, and even the beauty of mathematics beyond the classroom. Whether through articles, puzzles, or artwork, every piece here reflects the passion and curiosity of young minds. Learning happens not just in classrooms but also through discussions, creativity, and exploration. The Wall magazine stands as a testament to the lively mathematical culture of our department. At the helm of our department stands a leader dedicated to academic excellence, Professor Arun Kumar Tripathi, our esteemed head of the department. Guiding both faculty and students, Professor Tripathi ensures the smooth functioning of the department while fostering an environment of research, learning, and innovation. With a vision for progress and a commitment to excellence, our head of the department leads the department toward new academic horizons, ensuring that the legacy of mathematics at Sambalpur University continues to grow. But some teachers, even after retirement, continue to guide and inspire students. Here, we meet Professor Sabita Sahu, a renowned expert in algebra, who, despite retiring, remains deeply connected to the department. A passionate mathematician and a dedicated teacher, Professor Sabita Sahu has shaped the lives of countless students. Her expertise in algebra continues to enlighten young minds, proving that true educators never stop teaching. Her commitment to mathematics goes beyond retirement. Whether through lectures, research discussions, or mentoring students, Professor Sahu's presence in the department remains invaluable. Great teachers never truly retire, they continue to guide, inspire, and shape young minds. As we move ahead, we come to the heart of student interaction, where young minds receive mentorship, encouragement, and expert guidance from our esteemed guest faculties. Here, we meet Dr. Madhuchanda Sahu and Mr. Rajesh Kumar Sahu, two dedicated faculty members who not only excel in their respective fields but also connect deeply with students as mentors and guides. It was a quiet afternoon in the Department of Mathematics at Sambalpur University. The sun cast long shadows through the trees outside, and a gentle breeze carried the distant echoes of students engaged in lively discussions. Amidst this academic serenity lay the heart of the department's digital realm, the computer lab. In the mathematics department's computer lab, students and researchers work with LaTeX to draft research papers, project reports, and presentations. Welcome to Sambalpur University, a place where knowledge meets tradition, and aspirations turn into achievements. As we move forward through this lush green campus, we approach a hub of mathematical excellence, our Department of Mathematics. Established in 1969, the Department of Mathematics has been a pillar of academic strength, shaping young minds and advancing the frontiers of mathematical research. Step inside, where equations come to life, numbers tell stories, and every theorem unravels a new possibility. Welcome to the Department of Mathematics, Sambalpur University, a place where numbers speak, equations solve mysteries, and legacies are built. For decades, this department has been guided by brilliant minds, professors whose dedication and passion for mathematics have shaped generations of scholars. Here, we honor those who have dedicated their lives to mathematical excellence. From esteemed educators who have shaped the department to scholars making groundbreaking contributions in the field, this board is a testament to their impact. Their work continues to inspire, their teachings remain immortal, and their legacy lights the path for the mathematicians of tomorrow. Every name here tells a story of perseverance, discovery, and an undying love for mathematics. This board is more than just a collection of photographs. It evolves. Beyond research and teaching, the smooth operation of the department relies on this office, the center of all official activities, from admissions to academic records and student services. Every aspiring mathematician's journey at Sambalpur University begins here. From admission processing to course registrations, scholarship applications, and academic certifications, this office ensures a seamless experience for students and faculty alike. With dedication and efficiency, the administrative team works tirelessly to support students, helping them navigate the path of higher education in mathematics. But mathematics is more than just formulas and theorems, it is also about ideas, creativity, and expression. And here, at our wall magazine, students showcase their mathematical explorations, artistic insights, and academic reflections. This platform provides a space for students to share their thoughts, discoveries, and even the beauty of mathematics beyond the classroom. Whether through articles, puzzles, or artwork, every piece here reflects the passion and curiosity of young minds. Learning happens not just in classrooms but also through discussions, creativity, and exploration. The Wall magazine stands as a testament to the lively mathematical culture of our department. At the helm of our department stands a leader dedicated to academic excellence, Professor Arun Kumar Tripathi, our esteemed head of the department. Guiding both faculty and students, Professor Tripathi ensures the smooth functioning of the department while fostering an environment of research, learning, and innovation. With a vision for progress and a commitment to excellence, our head of the department leads the department toward new academic horizons, ensuring that the legacy of mathematics at Sambalpur University continues to grow. But some teachers, even after retirement, continue to guide and inspire students. Here, we meet Professor Sabita Sahu, a renowned expert in algebra, who, despite retiring, remains deeply connected to the department. A passionate mathematician and a dedicated teacher, Professor Sabita Sahu has shaped the lives of countless students. Her expertise in algebra continues to enlighten young minds, proving that true educators never stop teaching. Her commitment to mathematics goes beyond retirement. Whether through lectures, research discussions, or mentoring students, Professor Sahu's presence in the department remains invaluable. Great teachers never truly retire, they continue to guide, inspire, and shape young minds. As we move ahead, we come to the heart of student interaction, where young minds receive mentorship, encouragement, and expert guidance from our esteemed guest faculties. Here, we meet Dr. Madhuchanda Sahu and Mr. Rajesh Kumar Sahu, two dedicated faculty members who not only excel in their respective fields but also connect deeply with students as mentors and guides. It was a quiet afternoon in the Department of Mathematics at Sambalpur University. The sun cast long shadows through the trees outside, and a gentle breeze carried the distant echoes of students engaged in lively discussions. Amidst this academic serenity lay the heart of the department's digital realm, the computer lab. In the mathematics department's computer lab, students and researchers work with latex to draft research papers, project reports, and presentations. Welcome to Sambalpur University, a place where knowledge meets tradition, and aspirations turn into achievements. As we move forward through this lush green campus, we approach a hub of mathematical excellence, our Department of Mathematics. Established in 1969, the Department of Mathematics has been a pillar of academic strength, shaping young minds and advancing the frontiers of mathematical research. Step inside, where equations come to life, numbers tell stories, and every theorem unravels a new possibility. Welcome to the Department of Mathematics, Sambalpur University, a place where numbers speak, equations solve mysteries, and legacies are built. For decades, this department has been guided by brilliant minds, professors whose dedication and passion for mathematics have shaped generations of scholars. Here, we honor those who have dedicated their lives to mathematical excellence. From esteemed educators who have shaped the department to scholars making groundbreaking contributions in the field, this board is a testament to their impact. Their work continues to inspire, their teachings remain immortal, and their legacy lights the path for the mathematicians of tomorrow. Every name here tells a story of perseverance, discovery, and an undying love for mathematics. This board is more than just a collection of photographs. It evolves. Beyond research and teaching, the smooth operation of the department relies on this office, the center of all official activities, from admissions to academic records and student services. Every aspiring mathematician's journey at Sambalpur University begins here. From admission processing to course registrations, scholarship applications, and academic certifications, this office ensures a seamless experience for students and faculty alike. With dedication and efficiency, the administrative team works tirelessly to support students, helping them navigate the path of higher education in mathematics. But mathematics is more than just formulas and theorems, it is also about ideas, creativity, and expression. And here, at our wall magazine, students showcase their mathematical explorations, artistic insights, and academic reflections. This platform provides a space for students to share their thoughts, discoveries, and even the beauty of mathematics beyond the classroom. Whether through articles, puzzles, or artwork, every piece here reflects the passion and curiosity of young minds. Learning happens not just in classrooms but also through discussions, creativity, and exploration. The Wall magazine stands as a testament to the lively mathematical culture of our department. At the helm of our department stands a leader dedicated to academic excellence, Professor Arun Kumar Tripathi, our esteemed head of the department. Guiding both faculty and students, Professor Tripathi ensures the smooth functioning of the department while fostering an environment of research, learning, and innovation. With a vision for progress and a commitment to excellence, our head of the department leads the department toward new academic horizons, ensuring that the legacy of mathematics at Sambalpur University continues to grow. But some teachers, even after retirement, continue to guide and inspire students. Here, we meet Professor Sabita Sahu, a renowned expert in algebra, who, despite retiring, remains deeply connected to the department. A passionate mathematician and a dedicated teacher, Professor Sabita Sahu has shaped the lives of countless students. Her expertise in algebra continues to enlighten young minds, proving that true educators never stop teaching. Her commitment to mathematics goes beyond retirement. Whether through lectures, research discussions, or mentoring students, Professor Sahu's presence in the department remains invaluable. Great teachers never truly retire, they continue to guide, inspire, and shape young minds. As we move ahead, we come to the heart of student interaction, where young minds receive mentorship, encouragement, and expert guidance from our esteemed guest faculties. Here, we meet Dr. Madhuchanda Sahu and Mr. Rajesh Kumar Sahu, two dedicated faculty members who not only excel in their respective fields but also connect deeply with students as mentors and guides. It was a quiet afternoon in the Department of Mathematics at Sambalpur University. The sun cast long shadows through the trees outside, and a gentle breeze carried the distant echoes of students engaged in lively discussions. Amidst this academic serenity lay the heart of the department's digital realm, the computer lab. In the mathematics department's computer lab, students and researchers work with latex to draft research papers, project reports, and presentations. Welcome to Sambalpur University, a place where knowledge meets tradition, and aspirations turn into achievements. As we move forward through this lush green campus, we approach a hub of mathematical excellence, our Department of Mathematics. Established in 1969, the Department of Mathematics has been a pillar of academic strength, shaping young minds and advancing the frontiers of mathematical research. Step inside, where equations come to life, numbers tell stories, and every theorem unravels a new possibility. Welcome to the Department of Mathematics, Sambalpur University, a place where numbers speak, equations solve mysteries, and legacies are built. decades, this department has been guided by brilliant minds, professors whose dedication and passion for mathematics have shaped generations of scholars. Here, we honor those who have dedicated their lives to mathematical excellence. From esteemed educators who have shaped the department to scholars making groundbreaking contributions in the field, this board is a testament to their impact. Their work continues to inspire, their teachings remain immortal, and their legacy lights the path for the mathematicians of tomorrow. Every name here tells a story of perseverance, discovery, and an undying love for mathematics. This board is more than just a collection of photographs. It evolves. Beyond research and teaching, the smooth operation of the department relies on this office, the center of all official activities, from admissions to academic records and student services. Every aspiring mathematician's journey at Sambalpur University begins here. From admission processing to course registrations, scholarship applications, and academic certifications, this office ensures a seamless experience for students and faculty alike. With dedication and efficiency, the administrative team works tirelessly to support students, helping them navigate the path of higher education in mathematics. But mathematics is more than just formulas and theorems, it is also about ideas, creativity, and expression. And here, at our wall magazine, students showcase their mathematical explorations, artistic insights, and academic reflections. This platform provides a space for students to share their thoughts, discoveries, and even the beauty of mathematics beyond the classroom. Whether through articles, puzzles, or artwork, every piece here reflects the passion and curiosity of young minds. Learning happens not just in classrooms but also through discussions, creativity, and exploration. The Wall magazine stands as a testament to the lively mathematical culture of our department. At the helm of our department stands a leader dedicated to academic excellence, Professor Arun Kumar Tripathi, our esteemed head of the department. Guiding both faculty and students, Professor Tripathi ensures the smooth functioning of the department while fostering an environment of research, learning, and innovation. With a vision for progress and a commitment to excellence, our head of the department leads the department toward new academic horizons, ensuring that the legacy of mathematics at Sambalpur University continues to grow. But some teachers, even after retirement, continue to guide and inspire students. Here, we meet Professor Sabita Sahu, a renowned expert in algebra, who, despite retiring, remains deeply connected to the department. A passionate mathematician and a dedicated teacher, Professor Sabita Sahu has shaped the lives of countless students. Her expertise in algebra continues to enlighten young minds, proving that true educators never stop teaching. Her commitment to mathematics goes beyond retirement. Whether through lectures, research discussions, or mentoring students, Professor Sahu's presence in the department remains invaluable. Great teachers never truly retire, they continue to guide, inspire, and shape young minds. As we move ahead, we come to the heart of student interaction, where young minds receive mentorship, encouragement, and expert guidance from our esteemed guest faculties. Here, we meet Dr. Madhuchanda Sahu and Mr. Rajesh Kumar Sahu, two dedicated faculty members who not only excel in their respective fields but also connect deeply with students as mentors and guides. It was a quiet afternoon in the Department of Mathematics at Sambalpur University. The sun cast long shadows through the trees outside, and a gentle breeze carried the distant echoes of students engaged in lively discussions. Amidst this academic serenity lay the heart of the department's digital realm, the computer lab. In the mathematics department's computer lab, students and researchers work with LaTeX to draft research papers, project reports, and presentations. Welcome to Sambalpur University, a place where knowledge meets tradition, and aspirations turn into achievements. As we move forward through this lush green campus, we approach a hub of mathematical excellence, our Department of Mathematics. Established in 1969, the Department of Mathematics has been a pillar of academic strength, shaping young minds and advancing the frontiers of mathematical research. Step inside, where equations come to life, numbers tell stories, and every theorem unravels a new possibility. Welcome to the Department of Mathematics, Sambalpur University, a place where numbers speak, equations solve mysteries, and legacies are built. For decades, this department has been guided by brilliant minds, professors whose dedication and passion for mathematics have shaped generations of scholars. Here, we honor those who have dedicated their lives to mathematical excellence. From esteemed educators who have shaped the department to scholars making groundbreaking contributions in the field, this board is a testament to their impact. Their work continues to inspire, their teachings remain immortal, and their legacy lights the path for the mathematicians of tomorrow. Every name here tells a story of perseverance, discovery, and an undying love for mathematics. This board is more than just a collection of photographs. footfalls. Beyond research and teaching, the smooth operation of the department relies on this office, the center of all official activities, from admissions to academic records and student services. Every aspiring mathematician's journey at Sambalpur University begins here. From admission processing to course registrations, scholarship applications, and academic certifications, this office ensures a seamless experience for students and faculty alike. With dedication and efficiency, the administrative team works tirelessly to support students, helping them navigate the path of higher education in mathematics. But mathematics is more than just formulas and theorems. It is also about ideas, creativity, and expression. And here, at our wall magazine, students showcase their mathematical explorations, artistic insights, and academic reflections. This platform provides a space for students to share their thoughts, discoveries, and even the beauty of mathematics beyond the classroom. Whether through articles, puzzles, or artwork, every piece here reflects the passion and curiosity of young minds. Learning happens not just in classrooms but also through discussions, creativity, and exploration. The Wall magazine stands as a testament to the lively mathematical culture of our department. At the helm of our department stands a leader dedicated to academic excellence, Professor Arun Kumar Tripathi, our esteemed head of the department. Guiding both
this group SL2G. So SL2G is the set of all 2 by 2 matrices with integer entries and determinant 1. And we have a space. Okay, for a modular form, we need to have a group and a space. In this case, the space is upper half, complex upper half. Okay, and then this group acts on X by this usual. So you must have seen this in complex analysis. A, B, C, D, Z going to A, Z plus B by C, Z plus T. Okay, so SL2G acts on this space. The group acts on this space. Okay. Now, so what is a modular form? So modular form means it is a, whenever we talk about modular form, so modular form of weight K, so K is an integer. K is an integer, so modular form of weight K on the group SL2G. So SL2G, whatever this group I define. So it is a function from upper half plane to C. So that means it is a complex valued function on upper half plane. And the first property is that it satisfies certain property. We said that this is a modular form, it satisfies certain property. So first is that it is analytic or holomorphic on the upper half plane. Second is that it satisfies certain transformation property. That means f az plus b by cz plus d. So since the group SL2G acts on X, so az plus b by cz plus d is again an element in X. And it says that up to this factor cz plus d by cz plus d power k, this is kind of invariant. Okay, that means suppose this term were not there, cz plus d power k, then it would be like f of az plus b by cz plus d is fz. Okay, that is not the case here. So we have term cz plus d power k. So this is called the transformation property. Okay, so and the third property is that it has expansion like this. So it has expansion. So it has expansion like this. This is called the Fourier expansion. So modular form of weight K on SL2G means we have 3 properties. First is that analytic on the upper half plane. Second is it satisfies certain transformation property. Third is that it has expansion like this, which is called the Fourier expansion. Okay? And if in addition A0 is 0, because it has expansion, the coefficients A and are called Fourier coefficients. if A0 is 0, then we say that it is custom. So modular form, if A0 is 0, it is called a custom. Okay, and then one can easily check that if we fix K, then Mk, this is a vector space, complex vector space. So this is finite dimensional vector space. So Mk is a finite dimensional vector space. That is the space of modular form of weight K. And Sk is the space of custom. So it is a subspace of Mk. So it is subspace of Mk. Again, it is finite dimensional. Okay. So we have defined modular form. Sk is a subspace of Mk. Sk is the element of Sk satisfies this condition that A0 is 0. Okay. So both are finite dimensional complex vector space. So what are the examples? So unless you have example, if you define certain things, and if there is no example, then there is no meaning. So always one should ask for example. So this is the first example generally people studies. Ek, it is called the Eisenstein series. So if k is bigger than equal to 4 and even, then Ekz is a modular form of weight. So Ek, so we have defined it. So one needs to prove this, but it is known that this is a modular form of weight k. What is Vk? Vk is the Bernoulli number defined in this way. Bernoulli number is defined in this way, and sigma k minus 1n is the divisor function. So the Bernoulli number appears in the coefficient as a coefficient of Ek. That means Ek has Fourier expansion. So this is given in terms of Fourier expansion. Okay, and one can see that this is not a custom because A0 is 1 here. A0 is 1, A0 is not 0, so this is not a custom. So Ek is a modular form, but it is not a custom. Okay, second example is Ramanujan delta function. So this is what Ramanujan studied. That Q, this is given in terms of infinite product and this. So Q is what? Q, I should mention here that Q, I did not say anything. Q is e to the power 2 pi I z. Q is e to the power 2 pi I z. Z is in the upper half. Okay, so Ramanujan studied this function, and this is a cusp form because one can see that this is a cusp form. Q0 is A0 is 0 in this case. So this is a cusp form of weight 12 on SL2. So this Ramanujan delta function is a cusp form. This is a modular form, of course, and it is a cusp form. Specifically, it is a cusp form because the constant term is 0. Okay, this is weight 12. Note that this is weight 12, and for each k even bigger than equal to 4, Eisenstein series is a modular form of weight k, and that is not a cusp. So what is the usefulness of modular form? So this is the quotation by Martin Eichler. So he said that the quotation says that there are 5 fundamental operations in mathematics. They are addition, subtraction, multiplication, division, and modular. Okay. So one will see that many places modular forms will automatically appear. Although a priori it does not look like it will be of any use in that kind of problem, but this will appear. So this is the quotation of Eichler, but whether we know anything where it has been used. So this is the famous Fermat's last theorem, so which was unsolved for around 350 years. So this was proved by Andrew Weil. So in fact, the last kind of results were proved by Andrew Weil, but there are many results which were proved by many mathematicians before, and then the last things which were unproved, that was done by Andrew Weil. So he proved it in 1994, and he uses modular form. And for that he got Abel Prize in 2016. So this is described as stunning advance in the citation of this Abel Prize question. Okay. So another place where this appears is that Robert Langland. So it's known for Langland program. So he got Abel Prize again in 2018, and he got Abel Prize because of his visionary program, which is called Langland's program. So which connects representation theory to number theory. Okay, and then the modular form can be seen as tip of this. So this is the starting point one can see in that program. Modular form is just a starting point, and then there are many more things in that program. So if potential. So here many people are, if you do a particular area, people think that you do not need any other area, but that is not true. If you see that here differentiation theory connects to number theory, and there are many more which will connect to different areas. So you should not be confined to just only your area. So you should also know about other area also, so that you can apply your research. Okay, so another problem was so this Marina Vyazowska. So she got field medal, one of the field medalists in 2022. So last ICM. So she got field medal for the spear taking problem, and there she uses the theory of modular. So if you look at many advanced things, advanced problems where modular forms are used. Okay, so and still people, I have quoted three main problems, but modular forms are used by theoretical physicists also. So like in string theory people use modular forms. Okay, so now, so still I have not come to what polynomial I want, because the title says the location of the zeros of certain polynomial. For that, we have certain thing called L series. So what is L series? So we have a modular form. So modular form means it has Fourier expansion. So if it has Fourier expansion like this, a n e to the power 2 pi l z. So that is Q, I am saying. E to the power 2 pi I z is Q, that is what I am saying. So if this is a modular form, then I have Fourier expansion and I have Fourier coefficient, an are called Fourier coefficient. So if I have Fourier coefficient, I can define L series corresponding to modular form, which is just summation n from 1 to infinity a n by n power s. Okay, so this you can consider as a kind of generalization of Riemann zeta function. So Riemann zeta function is just 1 by n power s. Summation 1 by n power s is Riemann zeta function. Here we are taking, like this you can generalize. So any sequence given, you can consider this series. Yes. Yeah, so like I am saying is that in case of Riemann zeta function, in that region it converges absolutely uniformly, so you can define analytic function. So here I am not mentioning anything, but in some region, so you get a half plane. So you get a half plane. It depends on n. If you look at it, depends on n, because for Riemann zeta function it is 1. So that is some constant, so you get del part of s bigger than 1. In this case, it depends on the bound on n. So therefore, in some region, in some half plane, this is defined. But what more we have similar to Riemann zeta function is that if you complete it like Riemann zeta function, this completed L function is meromorphic continuation to the entire complex plane with possible simple poles at 0 and k, and it satisfies the functional equation. So similar things are there in case of Riemann zeta function. Here something more we have. Here something more means like similar thing, but because we are considering different sequence, we have possible poles at 0, and in Riemann zeta function you have a pole, a simple pole at only 1, s equal to 1. Okay, so this is functional equation, and there the Riemann zeta function s relates to 1 minus s. Here s relates to k minus s. Note that k is the weight of the modular. And if it is cusp form, so if it is cusp form, we do not get meromorphic continuation, it is holomorphic continuation. You do not get any pole, singularity. So we get holomorphic continuation to the whole complex. Okay, so now the polynomial, we are moving towards the polynomial. So if f is a cusp form, so it has Fourier expansion like this. So I consider this capital Fz. Capital Fz is just an by, so if you look at small fz is an e to the power 2 pi lz. Capital Fz is just an by n power k minus 1. Again, note that k is the weight, always k is the weight. So this is Fz. So it is known that it satisfies certain property that, like in case of modular form, if you look at, so this is 0. If whatever I have written Rn is 0 in case of modular. If you look at like just use the definition transformation property for 0, -1, 1, 0 matrix. If you look at this is 0. But in case of capital F, it is not 0, but it is something Rf. What is Rf? Rf is some polynomial. Okay, Rf is some polynomial. Here k minus 2 and this is binomial coefficient. And this completed L value at n plus 1. So they appear as coefficient. Okay, so this is a polynomial of degree k minus 2. So Rfz is a polynomial of degree k minus 2, and this is called the period polynomial associated to the cusp. So this is called the period polynomial associated to the cusp. So now note that what I have done, I have taken cusp, small fz. Out of this, I have constructed capital Fz, another function defined in this way. And then I took this transformation property, that means z power k minus 2 f of minus 1 by z minus f. So this is a polynomial, Rfz. So this is a polynomial of degree k minus 2, and this is called the period polynomial associated with the cusp. So we have got a polynomial. So now the question is, what are the zeros of these polynomials? So that means we want to study the zero. So this was proved by Algundi and Raji in 2024. So they proved that if f is a cusp and more than that it is H eigenform. So H eigenform you can think of it as a special kind of cusp. I have not defined it. It is a special kind of